Hi, my name is Celaya, and in this video I will be presenting on how to design a compound parabolic concentrator or CPC in SOLIDWORKS as well as within Fred. Before getting into the modeling, I'm going to talk a little more about the compound solar concentrator and touch on the geometric definitions that come into play when designing these systems. So a compound solar concentrator is a non-imaging optical element that has become common in solar concentration applications, coming in both reflective and refractive forms. The element utilizes two intersecting parabolic curves that have been tilted such that the focal points of each curve become a defining bound for the exit aperture of the element. The following shows equations that define some of the key parameters of the concentrator, including entrance aperture radius, focal length, and height. I'll refer back to these frequently when doing some of the SOLIDWORKS modeling. Alright, I'm going to start by doing the SOLIDWORKS model. So before I do that, I'm going to define a few parameters for our CPC. I'm going to say that the acceptance angle is 30 degrees and that the radius of the exit aperture is 10 millimeters. Again, just arbitrary values for the demonstration. So using those two values and the equations discussed previously, I can calculate that the entrance aperture radius is going to be 20 millimeters and that the total height of the system is going to be 51.96 millimeters. So I'm going to go ahead and draw the center line for the total height of the system first. So we'll just draw this line. And you'll see that the parameters is highlighted blue for the actual length of that line, and I'm going to change that to 51.96. So that's the total height of our system. The next thing I want to do is figure out where this acceptance angle crosses over this center line. So I can do that by looking at sort of the geometry of the system. So I know, for example, my exit aperture has a radius of 10 millimeters. And then I know that this angle coming off of it is going to be 30 millimeters because that's the maximum acceptance angle. So I can figure out that the point where it contacts that is going to be 17.32 millimeters from this exit aperture. So I'm going to go ahead and draw that line in now. 17.32. And this line is basically just a marker telling me where that intersection with this center line is going to be. So I'm going to actually go ahead and draw in those center lines. Again, using geometry, this time on the top surface, knowing that this radius is 20 millimeters and that this new distance here where it's going to intersect this line is 34.64 millimeters. I know that this line, which is going to be at 30 degrees, which is that maximum acceptance angle, is going to be 40 millimeters long. And then I can go down and change this to 60. So I know that the acceptance angle is 30, but SOLIDWORKS measures from this x-axis here. So from here up, it's going to be 60 degrees. However, the acceptance angle is measuring from this center optical axis. So that's going to be an angle of 30 degrees. So we're right on point with that. Next, I'm going to draw in the radius for our exit aperture. So that's 10 millimeters. And the reason I'm drawing the bottom or the exit aperture and not the top aperture is because this point right here and the additional point that'll come when I mirror this over are the two focal points for your parabolic surfaces. So those are going to be important when drawing in those parabolic curves in just a little bit here. So I can go ahead and do mirror entities. You'll see that line 4 is already selected, which is this line here. I can go ahead and select this top line, and then I'm going to select this center line because that's the axis that I want to mirror everything about. So now you kind of have an idea of what the shape of our system is going to look like. Up here is our entrance aperture. And then down here is our exit aperture, and you can imagine some parabolic surface kind of connecting those two apertures together. So to do that, I need to figure out the focal length of our two parabolas. So we know that the focal point is going to be here, and using one of the previous equations, knowing our acceptance angle and our exit aperture, we can calculate that the focal length is going to be 15 millimeters. So I need that axis of our parabola to be along the same angle as this acceptance angle. So I'm going to click where the focal length is, or the focal point is, and then if I just touch this curve up here, you'll see it draw these yellow lines. Those lines are parallel to that initial line, which is really great because that's the angle that I need these two parabola axes to be at. So I can go ahead and change the length of that to 15 millimeters. And then I can go back and use the same mirror trick as before. You'll see that line 7 is already selected. Click on this center axis here. And there we go, we have a mirror. So next I'm going to add in our two parabolic surfaces. So if we go up to the ellipse tool, click down on it, you'll see parabola. So SolidWorks measures the parabolas out, or draws its parabolas out from its focal point. So we're going to start here, click, and then draw back, and you'll see it start to form an outline of that parabola. We're going to go back to where that vertex is, click it again, and it'll give you this nice outline of what your parabola will look like. If you click from this point here, and then sort of just draw back up, you'll reach a point where you hit that edge of that entrance pupil, and that's going to draw out the curve, one side of the curve of your parabolic concentrator. We're going to do the same thing on the other side. Again, drawing back up. And there you go, you have the basic shape of your compound parabolic concentrator. Now we can go ahead and add in our top and bottom surfaces. I'll just draw these straight across here. And then we can trim off any of the remaining tail ends of our parabolas because we no longer need them. We have our compound parabolic concentrator, which is this shape here. So now we can create two different types of concentrators. We can create the refractive one. So if we go ahead and we trim off half of our concentrator and then redraw in this top line and this center line. So now we only have half our concentrator. We're going to actually rotate this this sketch around this center line here, and that'll give us our solid shape. So if you go to revolve boss/base, you'll see that now it's selected around line 12, which is the center line, and it does a full 360 rotation around there, which gives us our actual CPC shape. So we're going to go ahead and press OK. So now if you wanted to leave it here, this is what you would model if you wanted to model a refractive CPC. So you're done with that. You can export it out to Fred or your other optical software as you'd like. Now if you would like a reflective one, you would need to create a shell. So to do that, we'll create a shell of 2 millimeters, which is somewhat thin, but that's okay. So we're going to go ahead and click this top and this bottom surface, and then we're going to do show preview. And what that's going to do is going to create a shell around here, but it'll cut out this top and bottom surface. So if we press OK, you can see that now we have our hollow parabolic concentrator. And we want to do this going outward so we don't take out any of that geometry that we just drew on the interior of this element. So we're going to go ahead and model the CPC in Fred now, and it will be a lot faster to model in Fred than it is in SolidWorks. Again, the benefit of SolidWorks is that you can do a lot of extra modeling around that CPC instead of just the optical surface itself. But for analyzing the optical surface, Fred is definitely the faster way to make it. So if you go up on this top bar here, you'll see a bunch of different surfaces that you can make. One in particular, this one, is a Create CPC surface. So if you click on that, you'll have this screen pop up, and you'll be able to see all the different parameters, just like we calculated, that are available for modeling your CPC. So if we change our input semi-aperture to 20, which is what we calculated, and then change our out semi-aperture to 10, we have the option to make it hollow or solid, and we'll leave it hollow for now. And then we also have the option to truncate the length, which is essentially shorten the total height of it if you needed a smaller CPC. So we're going to go ahead and apply those. And you'll notice that if you scroll down, input of 20, output of 10, and those are the semi-apertures, of course. You'll see the length of the system is 51.96, which is what we calculated. The acceptance angle is 30, again, what we calculated. And the focal length is not 15 like we calculated. And that's because we calculated the focal length of each of those parabolas, where this is calculating the focal length of the system as a whole. So now that we have our system sufficiently modeled, we can go ahead and apply this. And you'll see that it creates a nice hollow CPC for us. And you can do the same thing with a solid one if you wanted to do a refractive element, and then go ahead and do all of your illumination testing on this surface.